Howdy, we are the Robotic Standing Team. Our sponsor is Dr. Pagilla, and our team members include Justin Wolf, Josh Tremblay, Jesus Gonzalez, Curtis Davis, Rick Wang, and Aldo Benavides. Dr. Pagilla is a professor here at Texas A&M. His main research interests are autonomous vehicles, robotics and mechatronics, and controls of nonlinear dynamic systems. As seen in his recent publications, our project will be focused on robotic surface finishing processes. Our senior design project was aimed at improving the research capabilities of Dr. Pagilla's lab by providing a means to conduct more controlled experiments concerning surface finishing applications. The current methods used in the lab employ the use of a random orbital sander mounted on a UR5 robotic arm. While this equipment can be used to run simple tests, it does not give the researchers the desired amount of controllability in their experiments. The previous equipment did not allow the researchers to vary the rate of particle removal from a surface in a controlled manner, and the random orbital sander produced a sanding motion that is difficult to mathematically model. To address these issues, the team aimed to design a robotic end effector optimized for the UR5 robot to aid in the research of surface finishing operations. The design phase began by sending a customer needs survey to the research team. Based on the gathered information, a hazard quality was used to give each need a metric and a goal. These metrics and goals allowed us to build a black box model which aided the team by indicating what the design had to accomplish. Next, a functional model was created, shown on the top right, to provide a detailed look at how the design would accomplish these goals. After brainstorming, members combined different ideas into a morphological matrix. Using the matrix, each member combined ideas they preferred into full designs that accomplished every task. These designs are evaluated using a Pew chart which compared how well each design would accomplish each task relative to the existing prototype, as well as two evaluation matrices that use quantitative data to compare design performance. The best design was chosen by comparing the results of these methods. After going through the design phase of the project, consulting with the research team, and reading published research papers, it was determined a rotary orbital motion was desired. This is because a mathematical model of the motion can be easily simulated and compared to the experimental results, unlike the random orbital motion originally being used. To achieve this motion, a planetary gear set was developed. The motion is generated by the planet gears in a gear set which rotate about their own axes while simultaneously revolving about the sun gear. Knowing the gear ratios in the system allow the researcher to simulate the trajectory of the sanding pads and understand which patterns produce the finest surface finishes. The gear set was designed to be modular, with interchangeable gears to give the research team the ability to add variability to their experiments in a controlled manner. A means to control the angular velocities and placement of the planet gears was provided to the research team so that they could adjust them as needed. A MATLAB program was created to give a simple way to calculate the ratios to be used. The modular design of the system allows the research team to utilize whatever gear ratio is needed. The gear set and gearbox are designed to be user-friendly, as the previous lab equipment was complex and took a long time to assemble. Our goal was to improve upon this by minimizing the number of parts and reducing the number of fasteners required to assemble the entire end effector. Additionally, the team took extra focus in designing the end effector in a modular way. This approach is preferred because it leaves the door open to future changes should the research team decide to change the focus of their research efforts. Wear and tear are a major concern for surface finishing operations because the tools are expected to endure hours of operation without failure. To ensure that our design would be robust enough to withstand hours of operation, an FEA analysis was performed. Our current prototype is shown here and currently does not include the housing that will support the motor to drive the mechanism. Here we show the mechanism in action by manually spinning the sun gear, thus driving the entire gearbox. It can be seen that the sanding pads attached to the planet gears follow the expected rotary orbital motion as designed. The motion produced here is different from the motion produced by a typical sander and is an area of research being conducted in Dr. Pagilla's lab. Our final deliverables were the following: a 3D printed prototype for end effector, a MATLAB code to calculate gear sizes, a motor speed calibration curve, and simulations of the sanding motion produced by our design. With the prototype serving as a proof of concept for the motion, we recommend the future components be made from PLA, aluminum, and steel.